Welcome back to the Home Lab, and today I'm going to show you an experiment that I think everybody should have done. And if you haven't done this at school, it's an easy experiment to do at home. What we're going to look at today is how to make a pinhole camera. Take a picture. 1, 2, 3.
Cheese.
So let's look at how to make the pinhole camera, and they're really very simple. At the end of the video I'll talk a bit more about how it works and the history of it and a few of my stories about using pinhole cameras. But to begin with, let's just look at a simple homemade or school pinhole camera. So camera means a room or a chamber, and they were often referred to as camera obscuras. So they were rooms that were dark, not dark rooms where you develop film, but a dark room. So all we need is a very small room that's dark. So I've got a cardboard box here. Children's shoe boxes work really well. And all you need to do is to cut a large hole in the front that can be covered up. So not the whole width of the front. And then the back, you completely cut the back out and stick a piece of grease-proof paper over the back. It's kind of baking paper, if you see what I mean. Tracing paper will do. So this acts as a screen, and this acts as the front of the camera, the bit that you're going to point directly towards the thing you want to take a picture of. Okay, so let's get ready to use our pinhole camera. So the problem with our box at the moment is it's got a very large hole at the front. So what I'm going to do is I'm going to cover the front up completely with a sheet of black paper. So there we go. And it can be quite tricky to get this to stay in place. So quite often I sellotape it onto the front. So behind that is the large hole, and it's now covered up with the black paper. So the other thing we need is something to look at. And in laboratories back in the day, they used an upright, that's a standing upright candle. I'm a bit nervous about using candles with large groups of kids in a room that's pitch dark with all the curtains closed and everything and the fire risk there. So I go back to sort of one of Edison's inventions, a really early type of light bulb. This is a carbon filament light bulb. You can use a very dim light bulb if you wish, or safely use a candle. That's not a problem at all. And finally, we need a pinhole. So I've got a large pin. I keep it in a block of polystyrene so I can find it and it's safely contained. And we're going to use this pin, any pin will do, these are called optics pins, to put one tiny hole in the front of the camera, and then we've got ourselves a pinhole camera. So we're ready to start our experiment. One or two of you might say, oh, there are better and different ways to do this. Yeah, I know that. This is the way I teach it, so I hope you enjoy looking at my method. And it's a really good lesson in, does the physics work? Doesn't it work? How can we improve things? And you'll see what I mean by that as we go along. Right, so pinhole camera. You can do this in the darkened room if you want, but just to show you, I'm going to get started by putting one single pinhole in the front of the camera. Now remember that this is the screen, and I've had students put pinholes in that. That's the bit you're going to look at, okay, when we've got the carbon filament lamp switched on, and this is the front of the camera. So here we go, one pinhole in the front of the camera. And what we need to do now is go into a darkened room, switch on the carbon filament lamp, point the camera at it, and see what we get on the screen. So we're now in the darkened room and we've got the carbon filament lamp on. So I'm going to point the pinhole camera at the carbon filament lamp. So it's got one small pinhole in the front, and let's see what we can see on the screen. So at this stage, I usually ask my students, describe what you can see. And after a while, they move backwards and forwards and they get a good image on the screen. They notice things like as they move closer, the image gets much bigger, and as they move further away, the image gets smaller. They notice it's very dim, it's not very bright. if they look carefully, they notice that the filament is upside down. The filament is inverted. And so what I get them to do is I get them to turn the camera upside down, and of course it makes no difference. The image stays inverted on the screen. So we've got an inverted, very dim single image of the filament in the carbon filament lamp, and this really is a bit on the dim side to take a photograph. So I wonder how we can improve our camera and get some more light into it. So we got a really nice image there of the carbon filament lamp, and the only problem was it was very, very dim. And to give you a little bit of background on this, you might remember seeing pictures of people with cameras with like a black cloth over their heads because they were looking at a screen and the image was so dim they couldn't really see it in the light of the room, so they had to kind of cover up and produce their own dark space to see the image. So how can we fix this? Well, I often ask my students now, I kind of turn the lights on for a bit and say, stop what you're doing. How can we get more light into the camera? And after a while, someone suggests a really good idea. To get twice as much light into the camera, let's make another hole. So here we go. About 1 centimetre away, let's make another hole in the front of the camera. Now we've got 2 holes, and that should have solved our problem about getting more light into the camera. So we're back in the dark room now, and we're going to hold the camera up to the carbon filament lamp and see what we get. Well, this is usually a bit of a surprise to most students. We actually have doubled the amount of light into the camera. We've still got an inverted image on the screen of the carbon filament, but we've got 2 of them. So we're now going to have to explain how did we get 1 image in the first place, and now why have we got 2 images? We don't want 2 images, we just want 1 image. So perhaps this hasn't quite worked. But just for fun, I wonder what happens if we add 2 more pinholes. So there we go, we got more light into the camera, but the problem was we got 2 inverted images of the carbon filament lamp's filament. So it's at this stage I usually suggest to students to continue doing what they're doing. Some of them think I'm getting it completely wrong, but what I say is, okay, well, you've got 2 holes in your camera, can you add another 2 so you've got a sort of square pattern, you know, about sort of centimetre, corners of a centimetre square. So there's 1 more hole, and there's another hole. So we've now got 4 holes in the front of the pinhole camera, and go back to the carbon filament lamp and see what you see and see if it reminds you of anything. So here we go. Let's point our pinhole camera with 4 holes at the front at the carbon filament lamp. And if we do that, you'll notice we now get, as you might guess, 4 images. And the reason for doing this is I then ask students, where have you seen this before? And as the years have gone on, less and less people have been able to answer that question. But in fact, one of the places we used to see it was with cameras that had 4 lenses on the front. And what you did was take 1 photograph, but because you got 4 holes on the front, 4 apertures, and they had lenses, you got 4 identical images. And there you go, 1 click, a set of passport photographs. So we've got our pinhole camera with its 4 holes. We've made ourselves a really poor kind of passport photograph camera. Obviously today you just take 1 image and the computer just generates another 3. But if you look on Google and things like that, you might be able to see those old cameras that had 4 lenses on the front. So what's our real problem here? Well, our real problem is the image is so dim, the aperture, the hole is so small that we're not getting enough light in. So let's see if we can fix that problem. So we haven't got enough light getting into our pinhole camera. So the obvious thing to do is to make the aperture larger. If you think about cameras that you've seen around, not on a mobile phone, but sort of big cameras, they've got quite wide lenses. So I get students to take a pencil and pick any of the holes or make a new one. It really doesn't matter. Don't damage the screen, but push the pencil in and make a hole in the front that's sort of pencil size in diameter. Go back to your carbon filament lamp and see if we've fixed the problem. Okay, so here we go, back in the dark room, and let's point our fixed pinhole camera at the carbon filament lamp, and well, it's all a bit of a disappointment. As with a lot of science, we fixed one problem and created a new one. So we fixed the problem about the amount of light. We've now got a really large amount of light hitting the screen on the back of the camera. And remember, the screen in the real world would be the film. The trouble is, our image is completely out of focus. So we need to fix that problem. But before we do, let's get even more light into the camera. And the way to do that is just to remove the piece of black paper. And if we remove the piece of black paper, we've now got a vast amount of light going into the camera. But of course, the problem is it's really out of focus. So one problem fixed, another problem created. We've got lots of light going in towards our screen, but the image we get of the lamp is really blurred. It's really out of focus. Now, you might guess what we use to make the image focused. We use a lens, and this is a convex lens, so it bulges outwards rather than inwards, and it's quite a thin, low power convex lens. And what we're going to do is we're going to go back to the darkroom, point the camera at the carbon filament lamp, and then use the lens to focus the light. And the way you do that is put the lens in front of the camera, and then you have to fiddle a bit and get it in the right place. Remember that this lens, if you look carefully, creates the image we want, but it doesn't magnify. So let's go back to the darkroom, see what happens. So here we go, let's point the camera at the carbon filament lamp, and you'll notice that the image, as we said, is really bright but very out of focus. And now let's put the lens in front, get the lens in the right place, and you'll notice it does something really clever. It takes all that jumbled up out of focus light and brings it to the right places on the screen, so we get one single inverted bright image. It's not magnified or reduced by the lens. All the lens does is focus the image. So we've now got a camera that really could work. So now for the bit that I find really exciting, and I think students do too, because they haven't really drawn the connections between the camera and using it properly. So what we then do is keep the lights fairly low in the room, but open one of the curtains and go up to the window and take our pinhole camera with its focusing lens and point towards the window. And when we do that, students are usually astounded by what they see. Okay, so now let's take the pinhole camera with its large hole and point it out the window. And as you notice, it's a pretty blurry image, but let's take our convex lens now and put it in front of the camera. And there you go. It's not the easiest thing to film. It's much better if you're actually here in the lab, but there's quite a nice image there, inverted you'll notice, of the trees outside my window. So all we really need to make this a real camera is some film on the back that would pick up that light, and then we would have a permanent photograph. So when doing this in the laboratory at this stage, I used to do a few silly things with the students. I used to stand up on the window, which was part of the lab bench, and sort of wave my hands and things like that to make it clear that the image is definitely inverted. And we've now got a working camera. You might worry about the fact that the image is inverted on the film that we could have in the back. But of course, you can turn that film upside down, or if it's the kind of film that's negative, when you develop it in the darkroom, the enlarger will invert it again and make it look upright. So the history of the pinhole camera is a very long one, or at least of the camera obscura, so we have to go back earlier than the invention of film, to well before 1000 BC. In fact, there seems to be evidence, sort of prehistory evidence, of the use of the camera obscura, which is basically a single pinhole with the sunlight shining through and then the image projecting onto the back wall, possibly of a cave. There is some talk of the ancient cave paintings looking a bit distorted and twisted and having been done in this manner. In other words, a light coming through, image on the cave, and then being traced out. I'm no expert in this field, but I think that's complete nonsense because, of course, the image would be inverted, wouldn't it? It'd be upside down, so that doesn't make sense to me. And then later on, work was written about how the pinhole camera actually worked. And of course, then we got film. And when film came along, we could capture the image permanently. And the camera developed, and this is a pretty ancient camera. I think they started making these in about 1901. This is a Kodak box brownie. Now, it's not quite a pinhole camera, but it's pretty close. If you look at the front, that's where the light goes in, and the back here would be the screen or where the film was. And it was one of these cameras, the Brownie Model 2, that was actually used to take those photographs of the Titanic when it was sinking and the iceberg that it actually hit. And thousands of these were made, and they were used particularly by children who started their interest in photography. So, as ever with me, a quick story about the pinhole camera, and I hope you find this amusing. So, back in the day when I was teaching these, I was quite interested in photography, and I had my own darkroom in the school. So I used to load these cameras with one sheet of photographic paper, get the students to take their pinhole cameras outside and then put them on the wall, and then when they wanted to take a photograph, they'd put a hole in the front, run up to be in front of the camera, stay there for a while, and then come back, put their finger over the pinhole, and we go back to the darkroom and develop the image. But of course, with all these experiments, you need to trial them first. And so I built a pinhole camera, put some photographic paper into it, and during a free lesson, I went outside, I put the camera up on the wall, and then I knew that the light level was such that you have an exposure time of, not click, exposure time of about 30 seconds to a minute. So I got a lab stool and I went back about 8 meters and I just silently stared at the camera without moving. Because obviously if you move, there's going to be a bit of a blur. You might have seen those very old photographs where the dogs in the front of the family are a bit blurred because they're moving around and everyone else is standing there very firmly because they've been told to keep still. Anyway, it was really quite funny and a little bit embarrassing. Someone obviously saw me from their classroom window, one of the teachers, it was an art teacher, and he came rushing out, and what he saw was me just staring blankly, sitting on a wall. Didn't see the pinhole camera. And he kind of came up, put his hand on my shoulder and said, "Look, are you okay? Is everything all right?" You know, he thought I completely lost the plot. And I said, "Yeah, not moving." And of course, I then went back and got the camera and explained to him what was going on. And he was really amused. But what was fun about that was, I haven't got the image anymore, but there I was sitting in the picture. And there was this ghostly image that came in and left. That was him coming to see me to check that I was okay. So let's quickly explain what we saw in our experiments and how the pinhole camera worked. So I've drawn some pinhole cameras here, and here's the first pinhole camera with the screen that you're looking at, a pinhole here, and this arrow represents the candle or the upright bright object, in other words, the carbon filament lamp. So if you think about it, light can come off the carbon filament lamp in all directions. But if you look at those rays, only from the top of the filament, the only ray that can get in through the pinhole is this one. So that will give an image of the top of the carbon filament. But what about the bottom? Well, rays will go off in all directions, but the only ones that can get in are going this way. So you can see they cross at the pinhole. And if you look at that carefully, the correct way to do this is to say that's one ray, and that's a second one. I'm not going to bother to continue to do that. But here's the top, and there's the bottom. So that's the top of the carbon filament or the candle, and here's its base. So you can see very clearly that the image is inverted, and it's also very dim because hardly any light from the whole filament makes it in through the hole. So now, if you understand that 2 holes is fairly obvious, that light from the top of the filament will get through that hole that way, and from the base of the filament this way. Got to be careful to show them crossing over. So what we've got there is our inverted image of the filament, but we do indeed get twice as much light in with a second hole, but of course we get a second image. So there's light from the top, and there's light from the bottom of the filament. So the way I've set it up is we get a second image here, and if you remember, we had 2 images at one stage, and then we made 4 holes and we got 4 inverted images next to each other. So here goes for the wide hole. Now this one's much better because it lets much more light in. So we'll get some light from the top of the filament here, and what I tend to do is draw the inverted top of the filament. Oh, and here, and here, and many other places. So you get lots and lots and lots and lots of the top of the filament. But don't forget, you'll also get lots and lots of light from the bottom of the filament. So the overall effect is to make the image much brighter, but of course, if you've got the bottom here and the bottom there and there and there and there and there, you'll get lots of tops and lots of bottoms, so the whole thing just appears completely out of focus. So finally, how does the lens help things? Well, you have to pick the right lens, so it has to be convex, in other words, bulging outwards on at least one side. And I'm not going to go into detail about how lenses work today, but suffice to say that this bit of the lens here is completely flat. So any light that goes through there does not get bent, does not get deviated, it just goes straight through. And the same for light that travels this way. This is an oversimplification, but you get the idea. So we've got light from the top of the object there and light from the base of the object here. And let's just continue this process. Well, what about light that hits the middle of the lens and comes from the middle of the object? Well, that goes straight through, so that's in the right place as well. But here's the clever bit. What about light that was heading up this way? Well, in fact, the way I've drawn it is it probably wouldn't even make it into the camera. But the effect of this curvature on the lens is to bend it downwards, and if you get the right lens, it will bend it down to the right place. So that brightens that point, and that light has come from the top of the bright filament. And you can draw other ones. In other words, this one that comes here hits a piece of glass that's not quite as curved, and that will bend down to the right place. And the same applies for rays that come from the bottom of the object. Hit a curvature that curves in the other direction, so bends, refracts, deviates upwards. And the diagram gets a bit complicated now. We need to do a video on lenses, really. But you'll notice that the lens sends all the rays that are coming towards the camera and hit the lens to the right place. And so you get more and more light hitting the back of the camera. And so you get a really bright, inverted, in focus and colour image. So there we go, the Pinhole Camera, a wonderful experiment, and I hope you found that video interesting. As ever, there is so much more than I can say, but I think it's probably time to stop now. So, do hope you enjoyed that. I'll be making another video soon. Do subscribe and like the video if you feel you want to, and you could buy me a coffee if you're feeling really generous, but don't feel that you have to. Anyway, I look forward to seeing you again next time.